Namaskar. Dear students, in this second video, we will discuss how to derive the expression for moment of inertia of discrete system and moment of inertia of two continuous systems, that means a ring and a rod. We are aware about the definition of moment of inertia and the formula for the moment of inertia of discrete body. The moment of inertia I is equal to summation over I from 1 to n mi ri square. And we are aware about the moment of inertia of a continuous body. In the last video we have observed, suppose di is the moment of inertia of certain mass element, then we will have to integrate to cover entire body, and that integration di is nothing but the moment of inertia of the complete body. Now first of all we will discuss how to calculate the moment of inertia of a discrete body. During the derivation of formula itself, we have observed that suppose there is a system of n discrete particles of masses m1, m2, m3, so on up to mi, then next particle up to mn, then every particle is performing circular motion with radii r1, r2, r3, dot 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 ri, dot 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 rn, and then the moment of inertia of the entire system is moment of inertia of each and individual particle, and we will have to take the summation. Therefore mi ri square is the moment of inertia of I particle. If it is single particle, then moment of inertia is this, and if there are number of particles, then I will have to take the summation. For example, suppose a particle of mass m is rotating about the axis with radius r, then the moment of inertia of this single particle can be written as I is equal to mr square, and therefore this can be treated as the basic definition of moment of inertia. It is the product of mass and square of the radius of revolution. Now I can say that suppose there are four particles, something like this. One particle is here, another particle is here, and third particle is here. To have the idea about what are the positions of the particle, I can say that they forms a triangle something like this. Okay, therefore this is the first particle, the second particle, and third particle. And if these particles are rotating about a certain axis, now I can think about different axes. For example, this distance is 3, this distance is also 3, and this distance is 2, suppose. And if I say that the axis of rotation is this can be treated as the axis of rotation. Therefore, if I am interested in moment of inertia of a system of these three particles about this particular axis, then I can say that if this is m1, this is m2, and this is m3, then actually there is no need to consider the moment of inertia of m1 and m2 about this axis. The reason is that for m1, the radius of circle or the position vector, the distance from the axis is 0, and therefore moment of inertia of m1 about this axis is 0. It is m1 into r square, but r is 0. Similarly for m2, and for m3 I will have to calculate this particular distance, this perpendicular distance. Now if I calculate this perpendicular distance, then I can find the moment of inertia about this axis of m3. It is m3 into this distance square, let it be a, and therefore I can write it is m3 into a square. This is the moment of inertia I of this system about this particular axis. Now how to calculate I? It is just the trigonometry. If two sides are 3, 3, this is 2, and then we can find this particular distance. There is no issue. Now if I am interested in moment of inertia about the perpendicular axis, that means suppose the axis is perpendicular to this, it passes through m1 and perpendicular to both this position vector, and suppose it is perpendicular to both this position vector. That means axis of rotation is passing through m1, and therefore there is no role of m1 to give the moment of inertia. Reason is that the distance is 0. But then about this axis, if I think about it is I2, if it is I, then I can write I2, the moment of inertia of this system about this axis I2 is equal to, see, it is m2 into 3 square plus it is m3 into 3 square. The reason is that m2 is rotating about this axis by keeping a distance 3 from the axis of rotation, and similarly m3 is also rotating by keeping the distance of 3. Therefore, what I will have to do, this is the moment of inertia of m2, this is the moment of inertia of m3, and I will have to take summation. Actually, there is m1 into 0 square, because the distance of m1 from the axis of rotation is 0, and therefore it is this, but this is 0, and therefore I have not mentioned that in the expression. Now, most of the time the problem will be asked something like this. Suppose 4 particles are there, they forms a rectangle or square. This particle is, this position is A, B, C and D. Now, masses of m1, m2, m3 and m4 are situated at 4 corners of a square. Then find the moment of inertia about the axis AB, suppose AB. Then we will have to remember that there is no need to calculate the moment of inertia because of m1 and m2, as m1 and m2 lie on the axis of rotation. Just we will have to consider m3 and m4. But suppose if it is asked to calculate the moment of inertia about an axis passing through the center and perpendicular to the figure, then I will have to find the distance, this distance, this distance, this distance and this distance, and then we will have to find the moment of inertia. That means we will have to take the sum. That means here I can write, if I am interested in moment of inertia about the axis of rotation, I will call this as I1. Then I1 can be written as, let the sides are of dimensions A, then I1 can be written as m3 into a square plus m4 into a square. This m3 is at a distance of A, m4 is at a distance of A, and therefore this. If the moment of inertia about the diagonal is asked, if I write this to be I2, that means moment of inertia about diagonal, then I will have to consider this distance, correct? This distance. I think this distance is a divided by root 2. Just I will confirm, it is a square divided by 2 plus a square divided by 2. That means it is a square and it is fine. It is a divided by root 2. This distance is a divided by root 2. This is also a divided by root 2. And hence, the moment of inertia I2 can be written as, it is m1 into a divided by root 2 bracket square plus it is m3 into a divided by root 2 bracket square. Now you may calculate this later on. Now, why only m1 and m3? Because m2 and m4 lie on the axis which we are considering for the moment of inertia. Suppose this is I3, then moment of inertia about this axis I3 can be written as, now here I will have to consider all, it is m1, because m1 is at a distance of a divided by root 2 about this from this axis. Therefore m1 a divided by root 2 bracket square plus I will have to write it is m2 a divided by root 2 bracket square plus I will have to write it is m3 a divided by root 2 bracket square, and plus I will have to write m4 a divided by root 2 bracket square. Now it depends on the situation. Therefore, most of the times the problem will be asked by giving the coordinates of the masses. For example, the masses of 2 kg, 3 kg, 4 kg, 5 kg are situated at some coordinates 0, 0, 1, 0, 0, 2, say for example 0, 1, 1 or 1, 2, 3, etc. And then we will have to draw the figure, we will have to identify the position of masses. Then we will have to find the distance of each mass from the axis of rotation, and we will have to use such formula to determine the moment of inertia of the entire system. It is fine. Now, if there is continuous system, now here we have considered the discrete masses. While considering the derivation for the moment of inertia also, we have considered discrete masses, that is m1, m2, m3. The separate masses are distinguishable particles. But suppose I will consider a situation where there is a rod, say for example. Okay, if there is a rod, something like this is a rod, then the rod is made up of infinite number of particles, and I cannot separate that, I cannot distinguish this first particle, second particle, third particle and so on. And therefore, an interesting technique is to be used. What we will have to do? We will have to divide this continuous system or object into small elements whose moment of inertia can be determined by using the basic definition, that is mr square. This is the basic definition, mr square. And for that, what I will have to do? I will have to divide this system into number of elements, small elements, which can be treated as a small particle, which can be treated as, for example, when we are considering the rotation of earth about the sun, we treat that earth is a single particle because the radius of revolution is so large as compared to the size of earth can be treated as a point, and we can say that it revolves around the sun like a particle. Similarly, when we think about the rotation of moon around the earth, we may treat this as a particle. But when we think about the rotation of the earth about its axis, we cannot consider earth as a single particle. We will have to consider it as a system of particles. Similarly, here we will try to derive the expression for moment of inertia of a rod about its axis, correct? About the axis passing through center. And for that, what we will have to consider? Let the mass of this rod is m and the total length of this rod is capital L. Okay. Now I will divide this rod into small segments, and I will consider one such a segment. This is a small segment of the rod, small part of the rod. It is at a distance x from the axis of rotation and whose width is dx. Correct? This is small element. Correct? Small element of the rod. Now, if m is the total mass and L is the total length, then I can define lambda to be the mass per unit length. It is very simple. It is total mass divided by length. And if I am interested in mass of this element of length dx, then that can be treated as dm, which is equal to lambda into dx. It is very simple. This can be treated as the linear mass density, and therefore what is the mass of the segment of length dx? It is density into the length. Okay, and therefore dm, mass of this small element, is lambda into dx. And now that is at a distance x from the axis of rotation. Therefore, moment of inertia of this element can be written as di, that is moment of inertia of this element only, is equal to dm into x square, because x is a distance. By using the basic definition of moment of inertia, that is moment of inertia of a small particle, single particle, is mass into square of the distance of rotation. And therefore for this element is rotating about the axis of rotation with radius x, and its mass is dm, therefore it is dm into x square. But now you will observe that depending on this mass, position of this dm, x changes. For this x is this x itself, but for this mass, x is minus L upon 2, because total length is L, therefore it is at a distance minus L upon 2, and this element is at a distance plus L upon 2, and therefore what I will have to do? To calculate the total moment of inertia, I will have to integrate dm over x from minus L upon 2 to L upon 2. Remember that here there is a physics. What we are doing, we should know. To cover the entire moment of inertia, that means to cover the entire rod to calculate the moment of inertia, what we will have to consider? We will have to consider the element which is at a distance minus L by 2 to the element which is at a distance plus L by 2, and hence we will have to integrate over x. Which term is changing? X is changing from minus L by 2 to L by 2, and therefore integration over x from minus L by 2 to L by 2 of what? Of di, that is moment of inertia of one such element which is at a distance x, that is variable, correct, that is x, and whose width is dx. Now I will substitute, this is nothing but integration over x from minus L by 2 to L by 2. I will write it is dm into x square. But what is dm? Dm is lambda into dx, because I cannot integrate over dm over m. Integration is over x. and hence I will have to convert the variable m to x, and for that the formula is there with us. It is dm is equal to lambda into dx. Hence I can write it is integration from minus L by 2 to L by 2. It is x square lambda dx. Now what I have done, I have rearranged the terms. X square first, instead of dm I can write it is lambda into dx, lambda into dx. Now as there is dx x itself, there is no need to write x is equal to. Here we were integrating di but changing x. Therefore I cannot write integration di from minus L by 2 to L by 2. Otherwise you can write integration di to be I and substitute L by 2 and minus L by 2. Therefore integration is over x. Therefore first of all we will have to change the variable from I to x. First of all I to m, then m to x, and now we can integrate. Now what is the integration of lambda x square dx? Lambda is constant and therefore integration is lambda x raised to 3 upon 3 from minus L by 2 to L by 2. We are aware about such type of definite integral. Therefore we will have to substitute for x to be L by 2, then minus L by 2, and I will have to take the difference. Therefore I can write this is lambda divided by 3. I can take this outside because it is constant. X to be replaced by L by 2, and therefore it is L cube divided by 2 into 2 into 2, it is 8, minus, I will have to substitute minus L by 2 instead of x, and therefore minus L cube, it will be minus L cube divided by 8, correct? And this can be treated as minus minus, it becomes plus. I will have to substitute lambda to be m by L, and hence I can write it is m by 3L. Then I can write L cube divided by L plus L cube divided by L, that is 2L cube divided by 8, correct? 2L cube divided by 8. And if I rearrange the terms, it is 1 upon 12, check kara, 1 upon 12, it is ml square. Therefore moment of inertia of a rod of length L about the axis passing through its center. Now why I am insisting that? If I am taking the axis which passes from one end of the rod, I cannot integrate from minus L by 2 to L by 2. At that time we will have to, either we will have to integrate from 0 to L, or we will have to use the parallel axis theorem, correct? That can be discussed later on. But here the moment of inertia of a rod of mass m and length L about a axis passing through its center is 1 upon 12 ml square, correct? Therefore this rod is continuous and I can calculate the moment of inertia of a rod like this. Now in a similar manner we will consider a ring. Now once the technique is known to us, it is possible to derive the expression easily. And if I am interested in moment of inertia of this ring about the axis which passes through the center and perpendicular to the ring, that is axis of the ring itself. Remember that so many axes are possible. I can treat the axis which is along the diameter of this ring which passes through the ring itself and parallel to this axis of the ring, etc., etc. We will discuss this later on. Now what about the nature of the ring? The total mass of the ring is m. Let the radius is r. Let the radius is r. And therefore the circumference can be treated as the circumference will be 2 pi r, and mass per unit length can be written as lambda is equal to m divided by 2 pi r. This will be the mass per unit length. The technique is same. Divide the ring into number of elements. That means if I divide the ring into so many elements, if I consider one such element, let the length of element is dx, or I will write it is dl. Any letter can be used. dl, length is dl, and it is at a distance r. It is at a distance r. Therefore what will be the moment of inertia of that element? For that we will have to calculate mass of that element. Mass of that element will be lambda into dl. Lambda is the mass per unit length, into the length of that element. Therefore, lambda into dl is mass of that element, and hence the moment of inertia of that element can be written as dm into r square. Correct? Dm into r square. Now, what is the total moment of inertia of this ring? I will have to integrate over di, correct, from one element, second element, third element, and so on again up to that element. And therefore here there is no need to change a particular variable, but it is close integration over L. L is changing. We are changing L not from a particular lower limit to particular higher limit. In case of a rod, x was changing from minus L by 2 to plus L by 2. It is not close object. But ring is the close object, and therefore L changes in such a way that we will have to consider a close object. Therefore this is close integration over length of di. Now as the integration is over length, I will have to change the variable from I to L by substituting the expression for moment of inertia. Therefore I will write here it is closed line integration of r square dm. But again I cannot integrate this as integration dm to bm because integration should be over the length. Therefore I can write that is to be equal to dm is to be substitute. Therefore it is integration over L. It is lambda r square dl. Correct? Lambda r square dl. It is fine. Now lambda is constant. Now in this case, for every element r is constant. See, here in case of the rod, depending on the position of element, x was changing. X was changing. But here the r is, and therefore see here it is x square. Dm x square was changing, x was changing. But here it is dm r square, but r is same for all element, and therefore that can be taken outside the integration, lambda r square, and I can write it is closed line integration of dl. Mean just I will have to add dl plus dl plus dl plus dl and so on. And we know that if I add all the line segments, then it will be 2 pi r, and hence I can write it is lambda r square into 2 pi r, because integration over line, close integration over line is nothing but the circumference of a circle of radius r, and that is 2 pi r. Now I will substitute for lambda. Lambda is equal to m upon 2 pi r. Hence it is m upon 2 pi r into r square into 2 pi r. 2 pi r gets cancelled, and it is mr square. Therefore again I can write moment of inertia of a ring of mass m and radius r about its axis. It is axis of the ring itself that is passing through the center and perpendicular to plane of the ring is mr square. It is mr square. This m is capital. Remember that this is the entire mass of the ring, and capital R is the radius. It is not the mass of element. Therefore moment of inertia of a ring is mr square. Now here we will stop this video. For the next video, what we will have to do, instead of dividing the system into a single mass element, we will divide it into the element whose moment of inertia is known to us. And how to do it, we will discuss in the next video. Thank you.